No. Live. Very good morning to all. Welcome to the final day of our session. Today's speaker is Dr. Vinayaka Pandit. Dr. Vinayaka Pandit is a senior manager, senior technical staff member, and blockchain researcher at IBM Research India. He obtained his PhD in computer science from IIT Delhi in the year 2004. He is interested in design of algorithms, local search heuristics for combinatorial optimization, and mathematical programming. At present, Dr. Vinayaka Pandit leads blockchain solutions and multi-enterprise business networks research strategies at IBM Research. In this role, apart from leading the strategy for the division, he also directs the blockchain and supply chain research department at IBM India Research Lab. His current work brings advanced techniques from operations research, cryptography, security, machine learning, and blockchain together to enable privacy-preserving collaboration on multi-enterprise business networks. A leader in his field, we are fortunate to have Dr. Vinayaka Pandit with us this morning. He is going to talk about blockchain, privacy, and artificial intelligence. Now I request the speaker to deliver a talk. Over to you, sir.
Thank you, Professor Sushma, for the kind introduction. My name is Vinayak Pandit. I'm from IBM Research. And this talk is about blockchain, privacy, and AI. It sounds like a potpourri of ideas. And I hope there will be tidbits to kind of take home at the end of the talk. Okay, this is an area that we have been working on for the past few years. And I have kept the talk to be fairly basic, not making any assumptions about background knowledge, etc. So what we will do is we will start off with a brief introduction to blockchain. Okay, it's not going to be a technical introduction. It's going to be an introduction through examples. Okay, and if you have any questions, urgent questions, right? I mean, you might have a lot of questions, but urgent questions that you think will hinder your understanding of the rest of the talk, please feel free to ask questions. Okay, so we will begin with a simple example. I don't know how many of you work in supply chain or are familiar with issues that come up in supply chain, but here is a very basic issue that comes up in a supply chain coordination, right? So we have a simple situation where we have a manufacturer. We call this entity as M, and we have a suppliers, two suppliers, S1 and S2, and we have assembler T. Okay, and whenever I refer to these entities, sometimes I might refer to them as he. Wherever you feel comfortable, replace he with she. I do not mean to say it in any gender bias manner. Okay, and so the situation is very simple. So there is a particular component that a manufacturer gets made. This component is called C, and this component C is going to be made out of two subcomponents called A and B. Okay, and the way it is going to work is that the manufacturer is going to release purchase orders to these suppliers saying that ship 10 units of A to this assembler and ship 10 units of B to this supplier, to the assembler. And there will be another purchase order to T saying that assemble 10 units of this component C from the 10 units of A and 10 units of B, and then ship it back to manufacturer. Right? So this is the setting, and a very simple setting where the unit price of A is 1 rupees, unit price of B is 1 rupees, and unit price of assembling A and B together to form C is 5 rupees. Okay. So what happens, right? So if everything goes well, what would you expect? You would expect that S1 should get 10 rupees from M, S2 should get 10 rupees from M, and T should get 50 rupees from M, right? Now, as it happens in business, right? I mean, in traditional business settings, it is quite possible that M sends the following set of messages at the end of this transaction. M says that I have to pay 9 rupees to S1, 9 rupees to S2, and 45 rupees to T. Okay, so this is what M says, and now everybody is confused, right? This is different from what the expectation was, and everyone wonders, okay, what could have happened, right? So one scenario is that there was a component A that was faulty, right? And therefore, T could only assemble 9 units and send it back to C, right? So in this case, what should happen is that M has to pay 9 rupees only to the first supplier, but M has to pay 10 rupees to the second supplier. M has to, of course, pay 45 rupees to the assembler, right? And you should have a situation where T agrees that 1 unit of B is there with him for future assembly, and T also sends the faulty unit of A back to the supplier. This is one scenario. Another scenario is that reverse scenario, where there was a faulty component from B and T could only assemble 9 units, right? So the reverse of this situation should happen. There could be another situation wherein there was no faulty component from either S1 or S2, but there was an assembly error at C, right? In this case, M has to pay 10 rupees each to both S1 and S2, but M should pay 43 rupees to T because 45 rupees he owes for doing the assembly of 9 pieces, but T has actually wasted 2 units, and therefore that has to be penalized, right? There could be another scenario wherein there was no faulty component and all the 10 assemblies were good, and all the 10 assemblies were actually sent to manufacturer, okay? And one of the units got lost at the inventory of M, okay? And typically what happens in this kind of situation is that M is a very powerful entity, and M is able to arm twist others to say that, no, I only received 9 units and this is what I'm going to do, right? So this is, of course, a very, very bad situation to be in, right? So let's see what would we ideally like, right? Ideally, what we would like is everybody, right? Each one of these players is maintaining a ledger of all the events that are taking place, okay? And we have a guarantee that no one can unilaterally change just the copy of their ledger. If they try to do so, they will get caught, okay? And let's say we have contracts which automatically get executed when the ledger is in a particular state, meaning that when the manufacturer gets back the assembled parts, he has to pay the assembler. Whenever the manufacturer gets a message that a particular part was delivered to the assembler, he pays the supplier and so on, right? If that's the case, then when the manufacturer initially sends the thing, everybody's ledger looks like this, right? Everybody says that, okay, M released these POs to each one of these 3 parties. Okay, then the supplier 1 and supplier 2 starts their shipment, and that also gets recorded on the ledger, right? And now clearly, let's say assembler also has done this, right? So assembler has said that, okay, I have received these 10 units, right? So once the assembler does this, now let's say the assembler actually faces an issue where one of them is faulty, right? So he makes a faulty assembly, right? Now the assembler cannot send a wrong message, right? So if the assembler now says that, I only assembled 9 units, but I did not goof up with one, right? Others will be able to catch them, right? So this is the basic problem that this kind of a distributed ledger, as we call them, is trying to solve, right? So everybody is maintaining the ledger simultaneously, okay? And therefore, at some point in time, based on the convenience of just one party, that party cannot lie about the state of the ledger. They have to report the truth. Okay, so this is really what blockchain is really trying to solve. Okay, so it's basically a ledger technology. Okay, wherein the ledger is maintained in a distributed and decentralized manner. Okay, meaning each one of these parties, as we showed, was maintaining the ledger independently, right, without depending on others. Okay, and they don't assume that there is a trusted third party who is helping them to maintain the ledger. Okay, so that's the way it is. The ledger evolves through consensus of the participating parties, meaning anything that gets into the ledger here happens only when everybody consents that, okay, this message should go here, right? So as I said here, if the assembler here, right, wants to say that he shipped 10 parts, 10 valid parts, okay, but only 9 of them were valid, that will not be able to go there because the manufacturer M will not agree, right? The manufacturer M will raise a flag saying that no, one of them is faulty, right? So everything happens through consensus. And then there is a very important property called immutable, okay, meaning that the protocol which is followed for maintaining this ledger has this property that once something is written to the ledger, nobody can erase it. It stays there forever. Okay. And finally, the most important thing is that there is a notion of smart contracts, which is you can pre-register smart contracts saying that whenever the ledger is in a particular state, right? So you can think of this entire thing as a state machine. And when the ledger is in a particular state, automatically execute a particular action, right? As I said, whenever there is a message in which everybody agrees that a particular part shipped by a supplier is received by the assembler, the smart contract says that the manufacturer has to pay that money, right? And it happens seamlessly. No one can stop it from happening. Okay, so these are the properties that is given by the blockchain. Okay, so this is a protocol, a distributed protocol that executes over a network and provides these kind of properties for the participants. Okay, and why is it called a blockchain? Because the way the information is maintained is that there is a chain of blocks that get constructed as part of the protocol. Each block contains information, right, of the ledger, and they are chained together. And that's why this immutable property comes. Okay, so if you try to change something in between, once the chain has already been formed, the protocol will break. Okay, so this is the basic notion of blockchain. Okay, if you have any questions about this is a good time to kind of ask this, but I'll just give a brief history. Okay, so the first kind of blockchain protocol in the last few years was called Bitcoin. You people might have heard about it. right? So no one really knows who the person is who actually released this particular piece of software, right? A paper was released and a software was released. There is an author name called Satoshi Nakamoto, but no one knows who this particular person is. Okay, and now it is today the biggest so-called cryptocurrency in this world. Okay, and one funny joke here is that when the first transactions using bitcoins was made, nobody knew what its value is going to be, right? So there was one person who bought two pizzas in a restaurant, and he paid, and that particular shop was willing to accept bitcoin in return for pizza, and at that time he paid 10,000 bitcoins for those two pizzas. Okay, so just to give you a sense, today one bitcoin is equal to almost 20,000 US dollars. Okay, so this person ate the most costly pizza ever in the history of mankind. Okay, the next step in blockchain evolution was another protocol called Ethereum. Okay, and this was 2015. And what it did is it actually improved upon Bitcoin, right? In the sense that it truly enabled distributed applications through smart contracts for the first time on a blockchain network. Okay, and since 2015, a lot of businesses have seen interest in this technology, and you have seen we have seen a emergence of what we call as enterprise or permissioned blockchains, right? Hyperledger is one of the big ones. Corda is another one. Quorum, which is actually an enterprise version of Ethereum, is another one. Okay, and then we have a lot of networks which are meant for special purposes. For example, payment is a very popular application, and there are networks like Ripple and Stellar, which are used for payments. Okay, so in general, the blockchain is trying to solve this problem, right? There are multiple parties who have to collaborate, come together to solve some big business problem. In the previous problem, it was a bunch of suppliers, manufacturer, and assembler. But depending on the application domain, you will have different set of parties. They need to maintain a ledger, okay? And they, of course, desire that they're not placing trust in one particular party to run this network. Everything happens through consensus. There is provenance of everything that happens in the network so that you can recall what happened in the past. Immutability, meaning once there is something on the ledger, it is there for final. You don't take it back. Okay. So just to wrap up, shared ledger, smart contracts, consensus. We talked enough about it. But in the business world, we also require privacy. Let me go back to the example we had here. Okay. Here, as far as the transaction involving the part A was concerned, it is sufficient if the assembler, the supplier one, and manufacturer are in agreement, right? Supplier 2, S2, does not have anything to do with part A, right? And hence, this supplier may not want this supplier to have a view into this data, okay? And similarly, anything related to part B is something that the supplier S1 need not have a visibility into. Okay, so this type of selective provisioning or guaranteeing privacy from not leaking information to others is another aspect of business blockchains, which is not so prevalent in public blockchains like Bitcoin and Ethereum. Even there are certain privacy issues and there are privacy preserving protocols that have been designed, but this is a bigger issue when it comes to business networks. Okay, so before we go ahead, any questions?
I would just like to ask at this point, on one hand, we have blockchain for business strategies in some sense, as I understand. But then how does it relate vis-a-vis cryptocurrencies? How do two very different ideas come from the same, the genesis seems to be the same.
Yeah, so as I said, the right way to think about this is that think of blockchain as a protocol, right? A protocol which gives you these properties, right? You can maintain a ledger in a distributed and decentralized manner without trusting any one particular party. The protocol guarantees that everything happens through consensus, things are immutable once they get into the ledger, and that there are smart contracts. Now you can build different applications based on what you want to do. Okay. The entire premise of cryptocurrencies is that they do not like the idea of money floated by central banks. Okay. Why is that? That is because they feel that the central banks have arbitrary power in terms of how money is managed, right? So go back to 2008 when there was a big meltdown of financial systems all around the world, right? So what happened at that point in time? Almost every central bank just printed new money, right? So there was no asset that was backing up, new asset that was backing up this money, right? It was just that new money was printed so that that money can be distributed to the banks to save themselves, right? What does that result in? That results in, in some sense, devaluation of the assets that are actually backing up those currencies, correct? In some sense, suppose gold was backing up your currency, in some sense, you have devalued the value of gold, right? By just printing money without producing new gold as a backup, right? So they feel that this is highly objectionable, and hence cryptocurrencies think of this entire process of arriving at consensus itself as an asset, okay, as a effort that needs to be done to arrive at consensus. So there is a way to think about it, and hence they have a way of releasing new currency, new coins, so to speak, into the system in such a way that you cannot devalue the currencies that they are releasing into the network. Okay, and therefore, so that was the philosophical background with which the cryptocurrencies came into account. In short, they took this distributed protocol and applied it for building a currency that cannot be manipulated by a central bank, okay, or a centralized entity. Okay, so that was the philosophy. Now the same protocol can be taken and said, okay, let's try and solve a supply chain scenario. Let's solve a problem consisting of insurance companies who need to bring more transparency into the way insurance is managed, and so on and so forth. Okay, so there's nothing really puzzling about it. It's if you think of it as a protocol that can have different applications, cryptocurrency is one application, supply chain is another application, logistics is another application, financial services is another application, and so on. Okay, but as I said, when you are in a business setting, you need to do something separate, which is to make sure that the visibility is made available in a careful manner, unlike in Bitcoin, where everybody can see every transactions that takes place. Okay, hopefully that is clear.
Yes, that's fine, we can go ahead.
Okay. Yeah, so now let's come to what this topic really is about, right? So blockchain, privacy, and AI. Okay, so I think the first question that will come to your mind based on what I said and the example that I gave is, why should you worry about privacy in blockchain, right? The idea of blockchain is to build a distributed ledger where everyone can see everything, right? So then why bother about privacy, right? So this is a fundamental question that comes, okay? But as I said in response to the previous question, right? So this is a kind of simplistic view of blockchain. And the better way to think of blockchain, especially in business settings, is that it's a technology that brings together, complementary ecosystems, okay, that can achieve bigger value than they do in isolation. So we will see an example of this towards the end of the talk, okay? And invariably, what happens when you build a network like that is that several competitors are on the same platform. Even in the simple example I took, there are two suppliers who are in some sense competitors to each other, and they are on the same platform. Okay, and therefore there is a need to participate in the network while protecting private information from competitors. That is one, but that alone is it hinders the value of the network, right? You can say that I'm only going to reveal my information only to the party that I'm doing transaction with, right? Then in some sense it does not change the status quo, right? That is pretty much the way things currently are, right? So you want to break that status quo. How? By enabling mechanisms to reveal only the required information with collaborators, okay, as needed basis. For example, when C puts together, when the assembler puts together an assembled part, okay, can I provide a way by which A and B can come to know that, well, I supplied some of these parts, somebody else supplied certain other parts which had certain quality parameters, and all of them were used to put together this new component. Okay, so that kind of selective information sharing for collaboration is what is going to make blockchains realize the value in a broader sense. Okay, so now what we will do is we will try and understand these privacy concerns, right, in more detail, and also we will see what kind of solution concepts would one wish when we run into these kind of privacy settings. Okay, so here is a simple thing. Okay, so this kind of problem appears whether you're on a blockchain network or even in a day-to-day scenario. But the situation is simple, and hence you should be able to kind of appreciate this. Okay, let's assume that there is an applicant. Okay, and she wants to apply for a credit card to a credit card company. Okay, so the main question that the credit card company is worried about before giving a credit card is that does the applicant maintain sufficient balance, right? Because that's a very simple criteria and an essential criteria based on which credit card company will make this decision, right? The applicant today, how does it happen? The applicant will provide the bank statement for, let's say, last 6 months. Okay, and this satisfies the credit card company. They can look at it and see, okay, this is the amount of money she receives on a monthly basis, this is the amount of money she spends, and hence how much is the money she is left with, and so on and so on. Right? So this is fine. But what is the problem? The problem is that this reveals more than just the fact. Suppose the credit card company just wanted to make sure that on an average every month, the applicant maintains a balance of 1 lakh rupees. Okay, that's all they wanted to know. But here, they actually learn that she's maintaining not just 1 lakh, but actually 2 lakh balance every month. Okay, and they also get to know what are all the transaction patterns, right, of hers, right? Ideally, what would we like to do, right? So ideally, this applicant should be able to prove that I have some data which is exactly my bank statement. Okay, I will not reveal this statement to you, but I will give you a proof that this statement is authentic. Okay, and then I will give you a proof that this data which I am claiming to be authentic, right, is such that the balance every month is at least X every month. Okay, and in this entire process, the credit card company does not get to know what the exact balance is or what transactions have taken place, etc. But the proof is such that the credit card company is able to convince itself that yes, there is some authentic data as authenticated by, let's say, a bank. Okay, I don't get to see the data, but I have been given a proof which I can verify myself, which satisfies the property that I'm looking for. Okay, so this looks a little mysterious, but for now, just go with me saying that, okay, this is the kind of solution that you are looking for. Okay, so this is one example, simple example. Another example, now, we are getting into the network setting, right? Here is a very simple one. Okay, so this is a similar network as the one that we were discussing. Okay, there are many manufacturers. Typically, they are called OEM, original equipment manufacturers. OEM 1, OEM 2, OEM 3, and so on. There are different component suppliers. There is a quality certification body, and so on. Okay. And typically, what's the benefit of convening a network like this is that it provides connectivity. Okay, for example, it connects this supplier with this whole range of manufacturers. Suppose this this supplier is not doing business with this manufacturer, the network will enable such a connection in a seamless manner. Okay, so one of the simple thing that everybody wants to know is that do you meet my quality requirements, right? And different OEMs have different quality requirements. Okay, so how can this supplier satisfy each one of these OEMs with regard to his quality, right? So imagine that there is not just one supplier, right? There are many of his competitors also who are on this network, right? If this supplier just uploads all his quality data, which is verified or certified by this body, right? Each one of these guys can make sure that, yeah, this supplier meets my requirement. But the problem is everyone else gets to know the quality data exactly the way it is. Okay. So the question again is just like that credit card applicant. Can the supplier, right, make a claim based on some special hash of the data and a proof, right? Such that the OEMs are able to verify that the supplier's hash of the data, right, and the proof together is actually valid. Okay. And the access to the special hash and the proof does not allow them to infer anything else other than just the assertion that the quality requirement is met. Okay, so this is the second example. Now, there's a third example. Okay, so let's say there is a network that you are contemplating or you have already built where there are a bunch of insurance companies on the network. Okay, and the insurance companies have a big problem, which is that of fraudulent claims, right? So they would like to compute, right, based on real data, what's the average fraud rate in the industry. Okay, but because these are also competitors at the end of the day, they don't want, any one of these companies does not want others to really learn what is the fraud rate of each one of them, right? If you are an insurance company, you would like to know what the industry average is. Let's say industry average is 4%, but you don't want to reveal that your average is actually 6%, right? Or 2%, right? So you would like to know the average, but you don't want to reveal your fraud rate. That's the first thing. Second thing is that if they participate in a protocol to compute this average, the protocol should ensure that every participant gets the same output, right? So if we get the average to be 4, everybody gets the average to be 4. It should not be the case that I get an average to be 4 and someone else gets an average to be 5. Then it's useless. And of course, the third one is that the output actually equals the average fraud rate across all. Meaning, we all get 4, but the actual average rate was only 3. That should not be the case. If we all get 4, the answer should be 4. Okay. So this is what they would like to do. And a desired solution, how will it look like? It will be a trusted computation involving all these parties, okay, such that no party discovers the private data of others. Everyone gets the combined industry average, okay? And even if there are some small number of adversaries, right? Imagine there are 10 such companies, right? One of them is not behaving well. Even then, the protocol should work correctly, okay? So, any questions at this point in time in terms of what kind of privacy issues that we are trying to handle in the context of blockchain networks?
There are no questions from the participants so far, but if you could elaborate a little more on the question that you yourself asked, I think that would be good.
Which question?
That what kind of solutions we would expect in these scenarios?
Yeah. So the idea is actually that the next part of the talk will focus on how can we actually solve some of these problems, right? Especially think about it that each one of these things, right, sounds extremely incredulous, right? How can she convince this credit card company that she is maintaining a particular amount of balance every month without sharing the bank statement, right? And the credit card company is happy with it. It gets convinced also, but without seeing the balance and transactions, right? So each one of these things actually sounds like, how is this possible, right? How can they compute average without anyone learning what the number for others are, right? So all of this sounds like magic, right? And rest of the talk is going to be about unraveling some of these magics. Not everything, but to a large extent, you will kind of get, okay, what is happening here? Okay, so that's what we will do. Okay.
Right. Yes, right.
Okay. Now, I don't want to keep too much suspense, right? So I will give you the answers at this point in time, and then we will say how we do it. Okay. So what are the building blocks here, right? So we use blockchain. Okay. As I said, why? Because the blockchain in any collaboration, it gives you all these nice properties: consensus, provenance, immutable, smart contracts, a distributed ledger. Then we will use a particular component. I don't know, many of you might be hearing this term itself for the first time. Okay, we will use something called zero knowledge protocols. Have you guys heard about it? If you can take a poll or something like that. Okay. I am assuming most of you have not heard about it. Yes. So there is
we have a lag, a little bit of lag between, when you're speaking and the time participants get to hear.
Okay. Yeah, I can wait. I can wait if anyone is aware of this, at least the term, right? Even if they do not know what it means, there is a suite of protocols called zero knowledge protocols. Okay, it's a very nice area of cryptography. Okay, and we are going to actually use this to solve problems like this. Okay, that's why it is called a zero knowledge proof, meaning that you get a proof that some statement is true, and both the parties, she is the prover and credit card company is the verifier. The prover is happy to give a proof, verifier is happy with the proof, but the verifier learns nothing other than the correctness of the proof, no other knowledge. He gains zero knowledge. Okay, that's why it's called zero knowledge proofs. Okay, so I'll give you a simple example of what this looks like so that you can appreciate what it is. But yeah, so this is one big component in making those kind of things happen. The second is secure multi-party computation. Okay, and we will use this pattern for these type of scenarios where multiple companies, multiple entities on a network need to come together and do some joint trusted computation. Okay, so that's the big picture. Okay, and I also want to kind of give you, if there is one picture for you to kind of take home in terms of what kind of things are we trying to build here, right? Which is going to transform the way people collaborate in the real world is the following. Okay, you have blockchain powered industry networks. Okay, you might have a network which is bringing together a lot of companies which are involved in trade logistics. Okay, shipment, customs authorities, regulatory authorities, port authorities, land transportations, and these are depots, right? Depots and so on. So they bring all these kind of players on a network to give you information about where goods are, what is the state of goods, and so on and so forth. And you might have another network, which is, let's say, a food provenance network, wherein you trace a track of where all the food has come, right? So the food, the farmer grew a particular you start with something like, okay, what are all the inputs that a farmer uses to build, to grow a crop, and how that crop is actually collected by somebody, and then that crop goes to what are called aggregators, and there are consumer companies who buy things from them, and they actually then produce the food, and then it comes and sits in your retail store, and somebody brings up these kind of networks. Okay, and just building these kind of networks actually takes a lot of effort. Okay, so how things that we talked about, zero knowledge proof and secure multi-party computation, right? What are they going to do for us, right? They will do two things. One is they will make sure that the data that is shared is secure, okay? And this particular property, right, and protects business sensitive information. These two things is given by your blockchain networks itself. Okay, and what this does is it removes the barrier for the growth of networks. So people are willing to come to the networks because the networks provide these two properties. They make sure that the data that comes on the ledger is secure, meaning that nobody can hack into it and get it, right? And business sensitive information can be identified and protection mechanisms can be put. So this is given by the blockchain networks, as I explained earlier. What these protocols, zero knowledge proofs and secure multi-party computation, what they do is they will allow the participants to share sanitized derivatives of private data. Okay, what do I mean by this? What I mean is that go back to the example of the loan applicant, right? What is the loan applicant's private data? It is her bank statement. What is the derivative that she is going to derive? Is the month-end balance, right? So as long as everybody can be convinced that she has a sanitized month-end balance derived from the private data, you are good. Okay, so that's what things like zero knowledge proofs allow. And then analytics and AI based on such derived data, like the example of the insurance companies, right? So imagine, right? So in the insurance network, there are a lot of insurance transactions coming. Some are labeled fraud, right? Now, everybody derives their fraud rate as a derived data, and it's everybody can make sure that it's a sanitized one, and it still remains private. And then that private data is used for computing the average industry rate, and that's what is called analytics or AI based on such derived data. Okay, and once we do this, what does it do? It provides extra value for participants, right? So not only have the industry, like the insurance companies, right? They have come together on a network and they have made sure that their sensitive information is protected, the data is secure, everything. But they have also got this real-time data that the average fraud rate in the industry is 4%, which they would not have otherwise. Okay, so this is the big picture I want you to kind of take home. Okay, any questions on the big picture?
So if the industry takes an average, then the players who are playing better, who are doing better in business, etc., aren't they at a disadvantage?
Why are they at disadvantage?
Because when you take an average, so although let's say my default rate is let's say 2%, but everybody else is more than 2%. But when you
Correct.
take an average, even for me, you are going to consider it's 4 or 5%, whereas
No,
actually
no,
I'm
no.
doing better.
Exactly. So that's no. It's the other way around, right? So let's do this. Okay. Let's take this example. Okay. Let's say food provenance. Okay. And we are, let's say there are multiple farmers. Okay. There are multiple farmers, and the farmers, let's say in this, come together to compute what is the what can I say, spoilage rate for mangoes. Okay, supplied by all the farmers across. Okay, you know that, and let's say you get to know that the average spoilage rate is 4%. Okay, this is just information every farmer comes to know, right? Now the farmer who is at 2%, right, can enter into a private contract, let's say with Nestle, right, saying that, look, you can see this computation that has taken place on the network. Okay, and you know that the industry average rate is 4%. Okay, I will, if, and then I enter a contract with you which says that the price for my mangoes will be X if I meet just the industry average, and the price for my mangoes will be Y if my spoilage rate is, let's say, 20% less than industry average. Okay, so the farmer has still not revealed what his information is, right? But that information is useful for him to create a contract like this. Now, the value of his mangoes is not decided upfront, right? Nestle is also willing to enter into this, because in fact he can say that if my spoilage rate is higher than 4%, which is the industry average, then you can even penalize me, right? You pay me a price Z, which is less than X, right? So the farmer can enter into these kind of contracts, right, because he knows that relative to the industry average, he or she, right, is doing better. Okay, so that's the way you use your private information and public information to design these kind of smart contracts which will suit your business goals.
So essentially, available information can always be used to your advantage.
Correct.
Okay.
Yeah, and on the other hand, a farmer who is at 5% knows that two things. One, it's not good for that farmer to enter into some kind of a spoilage-based pricing mechanism at this point in time, and she also knows by how much she needs to improve, right, to actually be able to in future get into a situation like that.
Right.
Okay, so this is the big picture. I wanted you to get these things so that there's something to take home. Okay, now we will get into individual crypto. Okay, and what I will do is, I don't want to give you gory details of the state of the art zero knowledge proofs, state of the art multi-party computation, etc. Instead, what I want to do is, I want to give you a sense of how these protocols work with very simple examples that you can follow. Okay, so that's the goal. Okay, so zero knowledge proofs. Okay, and this is going to be fun. Just play this with me. Okay. What's an example of a zero knowledge proof, right? So here is a tree, and the knowledge here is going to be an ability of somebody to count the number of leaves in this tree. Okay, it's a very hard task, right? Everyone knows that it's a very hard task. So if there is somebody, right, who claims that, look, I can count the number of leaves in a tree, okay, then you call this person as a prover. Okay, she has made this claim that, look, he or she, right? I have used different pictures for the same prover. So the prover has made a claim that I can count the number of leaves. Okay. Okay, one way to do is for the prover to say that what is the number of leaves, right? And then for you to go pluck out every leaf in the tree and then get convinced that yes, the prover was able to count, right? And that's a hopeless task, right? There are so many leaves. Are you going to pluck each and every leaf and then make sure that, okay, the tally matched and so on and so forth? And also at the end of the day, you are not left with any leaf on the tree, right? So I want to give you guys maybe 30 seconds. Can you try to think how can, if you are the person who is trying to convince yourself that the prover's claim that the prover can actually count the number of leaves is, how would you design a protocol to make this happen? Let's just give a 30 seconds or a minute's break and see if people have ideas.
One way could be to pick up a sample.
Sample. Okay. But again, right? So see, this information is valuable to you, right? So I know that you basically care. That's a good idea to pick a simple, like pick a small stem and then ask, can you count the number of leaves?
Yes.
Yes, you could do that. And if I say 100 and if it turns out to be 100, right? I am giving you exact information on the number of leaves, right?
Yeah.
I only want to convince you that I have this capability. Okay, I don't want to tell you, I don't want to give you any additional information than convince you that I can do this task. In that case, how would I do it? That's a good answer. But, from an information revealing point of view, it reveals an information that I don't want to reveal. I only want to convince you that I have this power. And you also want to, you would like to know, right, whether that particular stem has 100 leaves. But as a prover, I don't want to reveal that. Okay. I will give the answer, but you guys think about it offline as well. Okay. So what happens is that I and you, we design a protocol. Okay. So the prover gets blindfolded. Okay. And you know why I have done this? Because I could not get a picture of the same girl also closing her eyes. So, okay. So the prover is blindfolded. Okay. And what you do, right? So you are the verifier, right? The verifier will decide, okay, will toss a coin and decide whether to pluck one leaf or not. Okay. The verifier decides either to pluck a leaf or not pluck a leaf. Okay, they will do that. And after that, they will again ask, okay, tell me whether I plucked a leaf or not. Okay.
Okay.
Now, if the prover indeed had the ability to count the number of leaves, the prover will know whether you plucked the leaf or not, right? Otherwise, the prover can at best do a guess, right? And there is a chance that the prover will fail. Correct?
Yeah.
Yeah. So this is the idea. Okay. So this is a zero knowledge. So suppose I get it right? Then you will say, well, you could have taken a random guess, right? There is a probability. You can do the probability computation, and there's a probability of half that you got it right? But then what we can do is we can repeat this exercise a few times, right? Say 20 times, right? Every time I get it right whether you have plucked the leaf or not, right? Then you have a lot of confidence. Yes, this person can indeed count the number of leaves on the tree. Okay. So this is what is happening in a zero knowledge. Okay. Essentially, the parties agree on a particular context. Okay. What is the knowledge? What is the claim that somebody wants to make? And they do that. And once they agree on the problem, and then they agree on the process, right? How are they going to interact to convince that the prover has a proof and the verifier is able to verify the proof? Okay. And the prover gives the proof, verifier receives the proof, and the verifier is able to convince the verifier that, okay, this is what happened, right? And why is it called zero knowledge? Because you didn't learn anything additional details than the verification of the claimed property of the private data. Okay. So these are some of the simple examples when you take a crypto course and somebody has to show you that zero knowledge proofs can indeed be constructed. They will take simple examples like this, or to show that you can provide a zero knowledge proof of a fact that a graph is whether it is three colorable or not, etc. Okay. But all of them have one problem, which is that there is a need for interaction between the prover and the verifier, right? They need to interact. And that interaction is not very desirable when you are trying to design real life applications. Okay. And therefore, there's a lot of research that has gone in designing protocols which have the following nature. One is that these proofs are non-interactive in nature, meaning that once the context is clear, right, and the context is not going to change, the proof is computed independently by the prover and can be verified by anyone. Okay, not just one verifier, but by any verifier. So this is a lot of innovation has gone into making it non-interactive. Second is a lot of research has gone into making the size of the proof succinct. Okay, in this particular example, the proof sizes were very small, but whenever you get into something which is slightly non-trivial and it has to be non-interactive, what happens is that the size of the proof becomes like really, really long. Okay, and a lot of work has gone in the last the first zero knowledge proof protocol was designed back in mid of 1980s, 1985, by a bunch of people at MIT, right? So in the last, and then the non-interactive versions were designed in the early 90s. Okay, so it took a lot of time to come up with a non-interactive proof. But then those proofs had this problem that these proof sizes were like really wrong, right? I mean, imagine that you have to put a very, very long proof on a blockchain network, right? It's going to be very difficult. So a lot of work has gone into making these proof sizes very succinct, okay, small proof sizes. Eventually, now we have a protocol in which the proof size is just 288 bytes, okay? Further, the process of both the proof computation and the verification should be efficient, okay? And just to tell you that all of this is possible using today's cryptography, okay? And they are called non-interactive zero knowledge proofs, okay? NIZKP is how they are called. NIZKP, non-interactive zero knowledge proofs, NIZKP, okay? So in practice, how does zero knowledge proof work, right? So initially, obviously, right? So here, because it was an interactive protocol, we agreed on a particular process, okay? In the non-interactive setting, what will happen is they agree on some kind of a setup information, okay? So they will talk upfront and say and establish a setup, okay? After that, what is going to happen is the owner, right? She has the secret data, right? She makes what we call as a binding commitment to the data, meaning that once she commits to this data, she will not be able to prove any false property about this data. That's why it is called binding, okay? And it's a special hash of the data, okay? Meaning the person who looks at this commitment cannot make out anything about the data itself. But he also is convinced that this is binding, meaning it will not allow this participant to cheat, okay? For example, right, if I compute the hash of a data and give you the hash, can I change my underlying data? I cannot, right? So we know that it's very hard, right? I mean, no one knows how to do it, to basically to take two data, both of which hashes to the same thing, right? So you have data, you hash it. If you give me the hash, and then I say, okay, did you really have the data? And if I give you a piece of data and it hashes to the same value that I gave you upfront, you know that, okay, I knew the data upfront, correct? So that's why it is called binding commitment. Now, this Bob is going to ask, okay, this is the property I'm interested in. Is your balance greater than 1 lakh at the end of every month? Then the prover gives a proof, and it actually looks like a very long random looking string, right? As I said, the most efficient one has 288 bytes, but there are certain proofs which are few thousand bytes, and there are some which are in fact tens of the megabytes and so on, depending on which protocol, right? So I give a proof which is a long random looking string. Now the verifier is able to take this commitment, this special hash of the data, and the proof to verify that Alice's data satisfies this property, right? So one simple thing is, if you forget the privacy aspect, right? We could just take any favorite hash function of yours, and I just do the hash of the data, and I say that this is my commitment. Okay. Bob asks, okay, is the monthly, this property true, right? Then here, what I would do, I would actually give you the actual data itself, and then this Bob can satisfy, because then he can see, okay, this is the hash function she used. This is the data she is claiming. Let me apply this hash function on this data. I'll get exactly the commitment she gave, and then I will check whether the data satisfies the property, and he's happy, right? This is not privacy preserving, but is an example of how binding commitment works, okay? And using zero knowledge proofs, you can actually do it in such a way that Bob learns the correctness of the proof without learning anything other than this data, okay? So this is kind of in a nutshell. I've given you on zero knowledge proofs, which is actually almost now 35 years of research. Okay, so now why has it suddenly become practical in the context of blockchain? As I said, we have come up with protocols in which You have to go through this setup only once instead of having to do every time. Okay. And as I said, the proof generation, proof verification, and proof size are all now amenable to be used in practice. Okay. And that's why it has become very practical now in the context of blockchains. So any questions on zero knowledge proofs?
There aren't any questions from the participants, but I would just like to ask you something. Does this mean that zero knowledge protocol is nothing but a diffused version of the information? Like you're not giving the entire information, but you are diffusing it with some parameter. Like you're not giving it day by day, but you're giving it over, let's say, weeks or months. So is that
No, that's not how it is. It is actually, as I said, right? This is the idea here is that I have some data that is private to me, right? Think of that as a knowledge that I claim to have, right? A zero knowledge proof is a way for you to let others, to prove to others that you have that knowledge without revealing to them anything more about that knowledge, right? And that's a very important thing, right? So for example, right, think of it like this, let's say you have as I said, a very special algorithm today that you have come up with, okay? And that algorithm, right, can solve, satisfy three sets, okay? And you want to convince Bob that you have this capability so that Bob can hire you at a very exorbitant salary to solve satisfiability problems. Okay. Now, how do you convince Bob that you have this algorithm which can solve satisfiability, right? One way is Bob says, okay, here is a satisfiability instance. Can you please give me a solution for it, right? You can run your algorithm and you can give the satisfiability answer, right? But then what if Bob actually had one challenging instance to solve? He has given you that only. You've given him the solution. He verifies, he's happy, he moves away. So you have not got any value from your special knowledge, correct?
Right.
Instead, zero knowledge proof allows you to convince Bob that, look, I have this magical power, but I will not convince you by actually giving you solution to any one of the problems per se. Right? You get convinced. After you get convinced, if you want to hire me, you hire me. Right? In the blockchain setting, we just twist it a little bit. Right? I have my private data. Right? And I will make a commitment to this data. Okay. In the example here, right, in the bank example, right, what we will do is, this is my bank statement, correct? Bank knows my statement, correct? So if I make a commitment saying that, look, here is some special hash, as I said, right? So let's assume that there is a special way of computing some hash, okay, of the data that everybody has agreed on, okay? So I compute a special hash of the data, of my data, my bank statement. I put it on the blockchain network, okay? Bank is going to look at that and verify and put a check mark saying that Alice has computed the special hash correctly. That's all she says, right? Now, Bob knows that the bank has agreed that this is the correct special hash of the data, okay? And now Alice gives a proof. And as I said, the proof looks like a random string, right? So Bob cannot make out anything from that. But there is a way, the way the protocol is designed such that if Bob takes this commitment and this proof, and then there is something called a verifiability circuit, and he puts these two things through that circuit, he will get either a 0 or 1. If he gets 1, it says that yes, the proof is a correct proof for the claim that is made. Okay, and that's the way we use it in blockchain. So it's not a diffusion of the information. It is there's no other way to say it, right? It's actually ability for you to make a claim about a particular private data and prove the property of that private data without revealing anything other than the truth of that statement.
Right. Got it.
Okay. Now, what will be the game? The game will be, we will look at secure multi-party computation. Okay. So, let's actually jump into the example itself. Okay. So here there are, as in all cryptographic protocols, there are always Alice, Bob, Carol. These are the characters. Okay, and they all have come together. Okay, it's exactly the same problem as the insurance companies. Okay, everybody wants to compute the average salary amongst these three people. Okay, and obviously, no one wants others to learn what their salary is. Correct? But they want to make sure that the average computed is correct. Okay, and fairness, right? Meaning, if one person learns the average, everyone else learns the average. Okay, this is consistent with what I said about multi-party computation in past, right? Now, how do they go about doing this? All right. Again, it's a very, very simple thing. Okay. So what everybody is going to do is that they are going to take their number and split it into 3 secret shares. Okay, because there are 3 parties. So you can here, you can see here. So Alice is red, Carol is green, and Bob is purple, blue, whatever it is. Okay. So Carol takes 100 and splits it into 3 random shares. Okay, they have this random shares have this property that these are 3 random numbers such that all of them add up to her actual salary, 20, 10, and 70. Okay, and so you can convince yourself 20 plus 10 plus 70 is 100. Similarly, Carol has done her green shares, right? And these shares could be even negative. 20 minus 10, 190, right? So you add them up, it is again 200, right? And Bob has 180, and what he has done is 70 plus 90, 160 plus 20, 180. Okay, and these are random shares, right? So each of these numbers themselves do not reveal anything about the salary, right? For example, minus 10 has nothing to do with 200, right? 20 has nothing to do with 200, and so on, right? Except that 3 of them together add up to 200, right? Now, once they do that, okay, and then everybody keeps 1 secret share to themselves and sends 1 secret share each to others. Okay, so you can see Alice has sent 70 to Bob, 10 to Carol. Okay, and Carol has sent retained minus 10 with herself, sent 20 here, 190 here, and so on. Okay, now what is going to happen is that each one of them is going to add up the numbers that they got. Okay, 20, 20, 20. So Alice got 60. Carol got 10 minus 10, 90. She got 90. Bob got 70, 70, 190, 330. Right? So each one of them got this, and then they are going to add up the totals that they got. 330 plus 90, 420, 420 plus 60, 480. Okay, so they got the sum to be 480. There are 3 of them, and hence the average is wait, sorry, what happened? 60, 150.
160.
Oh yeah, 160, right? So the average to be 160, and then you can convince yourself that it is exactly 160. So this is 20 from here goes here, 120, 40 from here comes here, 1. So 160. Okay, so each one of them, look at their shares, right? She's got 20, 20, 20. Can she learn anything about anyone else's salary from this? No. Similarly, she has got 10 minus 10, 90. Can she learn anything about the other salary? No. And Bob also, right? He's got these shares, can't do anything about them, right? But as long as they stick to the protocol, they can actually make, like get this particular answer, right? So this is the basic idea in multi-party computation, which is that there are secret shares that are generated for private data, and then computations are arranged on these secret shares. Okay, and then the aggregate computation on the secret shares are aggregated to get the aggregate computation. Okay, and you need to do extra things to handle that. Okay, Bob could potentially try to cheat, or Carol could potentially try to cheat, etc. In this case, we assume that nobody is going to cheat, right? And all of this will mean that instead of working with numbers, we will work with what are called polynomials. Okay, and that's what is secure multi-party computation. Okay, and why has it become practical is that suddenly, in the last 10 years, there's a huge improvement in the performance of secure multi-party computation. If you look in 2009, okay, and you wanted to do just one AES encryption, right? It used to take 2 seconds, which is enormous period of time to just do one AES encryption. Okay, but today, you can do 10 to the power of 5 AES encryption. Where there are encryption, right? Somebody has key and somebody has the algorithm, and they have to do the computation, two-party computation. You can do 10 to the power of 5 AES encryption. This is one big performance improvement that has taken place. Second is people have written compilers that allow programmers to not know anything about cryptography to write what kind of multi-party computation they would like to do, and they translate it into a multi-party protocol, corresponding protocol. Okay, so it allows programmers to focus on what they want to do rather than how they have to do, right? So that's the second thing. So, and we have started getting highly efficient protocols, right? For special purpose models, like, if you want to compute decision trees jointly, if you want to do association rule mining, etc., you can do this. And that's what has basically allowed people to start using multi-party computation in practice. Okay. So any questions?
No, there aren't any questions so far.
Okay. So then what we can do is I'll kind of, bring it all together, right? How do these things come together in the context of blockchain, right? So, so far you have heard me talk about blockchain. So you understand blockchain, you understand privacy, okay? And you understand privacy preserving protocols, you understand zero knowledge proofs, you understand secure multi-party computation. Now, the last bit is about, okay, how do they come together for solving specific problems in blockchain context, right? So this requires you people to have a little bit of background, but it's okay. Okay, so let's say that we have two networks. Okay, we have a trade logistics network, as I explained in the past. So this is a network in which all trade logistics related information is going to be there. Okay, and specifically there is something called bill of lading, BL. Okay, which is basically a way for a shipper, like let's say a shipping company, to say that particular goods has been shipped onto my ship. Okay, so that's what this is, bill of lading. Okay, and there's another network which is trade finance network. Okay, so here is an exporter who has sent some shipment. Okay, it's got to go to the importer. So, it's going to take 2 weeks or 3 weeks for the importer to get it. And the importer has said that, I'm going to pay you within 6 weeks of getting it. And exporter has to wait for 8 or 9 weeks to get the payment, right? Instead, the exporter would like to say, okay, if the payment was for 100 rupees, he would like to go to a bank and say that, look, I have to get this, I am due to get this 100 rupees payment from this importer. Why don't you give me today 98 rupees? Okay. And when the importer gives 100 rupees, you keep that 100 rupees, right? I don't need that 100 rupees. This is called trade finance. And there's a separate network for trade finance. Okay. And we want this trade finance network, it should be convinced that, okay, there is a valid bill of lading based on which this exporter is making the claim. Okay. If it's very difficult to put all the participants on one network. Okay, that's why you have two different networks. And now this network needs to get a proof that, okay, this information is true, so that then the bank can decide to pay the exporter. Okay, did you get the picture here?
Yes.
Okay. Now, how can we use all the things that we have, right? So every data that gets submitted, right? So first what we do is we set up a zero knowledge proof mechanism across the two networks and all the participants. Okay. Then the trade logistics network. So think of bill of lading information as private data. Okay. It keeps putting special hashes of the different bill of ladings that it contains on its network. Okay. So it's like just like the bank statement. Instead of the bank statement, here the special hash of the bill of ladings are being committed by the trade logistics network. Okay. Then the exporter on the trade finance network says that, okay, I have this particular invoice and I have this bill of lading corresponding to that on the trade finance network. So exporter makes this claim, and the bank wants to make sure that this statement is true, right? All it does is it asks the exporter, it basically asks the trade logistics network to say, okay, is this true, right? That this bill of lading appears in your set of all the bill of ladings that you have committed. So basically, there is something called a membership proof. Okay, so basically a proof that you can commit a set, and then you can give a proof that a particular element belongs to a set, right? So, so then it basically this trade finance network is asking: does this element belong to your set? And the logistics network gives a proof that yes, that element belongs to the set. So in the process, what has happened is trade logistics network has not revealed the set of all bill of ladings, because not all bill of ladings may be required by this trade finance network. But at the same time, this trade finance network has learned that this bill of lading, which they care about, is there in the trade logistics network. Okay, so this one example in which trade, zero knowledge proofs comes together to allow two networks to kind of work with each other. Okay. I hope the example was clear.
Yes, yes.
Okay. Now, let's skip this. I don't want to spend, because I think we'll run out of time. We'll take just one more simple example. Okay. Here, right, there's a food provenance network. And, we'll go back to the same detail, the same example that we took, right? So everybody, so think of it like this. Every retailer, right, everybody has their private data, which is their data DI, and their spoilage details, right? How many, what was their spoilage rate at each one of them, right? So this particular retailer has a particular private data D1 and spoilage rate R1. has D2, R2, D3, R3, D4, R4. Okay. Now, what they want to do is they want to compute a decision tree which says that, okay, what are the conditions under which spoilage is going to happen, right? So that in this network, when the conditions are being tracked, you can predict whether something is going to get spoiled or not. Okay. So the way they reduce this is that they will reduce this to a multi-party computation of computing a decision tree on these data are D1, D2, D3, D4 with the spoilage flag. Okay. And once they get this model M, which is the decision tree model, everyone can use it to predict the spoilage during the transit. Okay. And as I said, today's multi-party computation allows them to compute a decision tree like that, and that's how they actually do it. So this is an example of how AI gets done using privacy preserving protocols. Okay, so I will kind of end here, right, with this summary, which says that we need to kind of consolidate the gains of this really mushrooming blockchain networks in the industry. Okay, and we need to do by addressing specific concerns about privacy, and we should allow the different networks to leverage information across the networks. Okay, and that's where advanced crypto comes, by giving sanitized trusted insights using zero knowledge proofs, as we saw, and then it allows multiple parties to come together and do joint computation. Okay, and at this point in time, at least in the industry, and I'm sure even in the academia, right, a lot of active research and experimentation is going on building secure AI on business networks. So let me stop here.
So, we have heard a lot about privacy in the last few days, especially in this FTP as well. So as the networks become bigger, I'm sure the complications and the complexity of the situation also becomes more. So, right now the examples that we saw in your talk were all related to very small networks or very small, we're talking about only 3 people or 4 people or, very small networks, as I said. So how does one deal with it as the number of people and the number of parties involved becomes more?
Actually, I did not make any comment about the scale at which these computations can be done, right? I think just for the illustrative purposes, I took small networks so that I can, draw out these networks on a chart and show it to you guys. But each one of these things actually scales on very large networks, right? Just to give you an example, right? There is a particular protocol called Zero Cache Protocol. It's called Zcash. Okay, if people want to search, you can search Z Cache, CASH. It's a protocol that is built on top of Bitcoin. Okay, what it allows people on Bitcoin network to do is, let's say I and you want to do a transaction. Okay, we don't want others to realize that I and you did a transaction. Okay, we don't want them to know our identities, one, and we don't even want them to know that, let's say, we exchanged 100 Bitcoins. Okay, now what do the Bitcoin participants need to know? They need to know the following, that there are 2 entities in this network who did a valid transaction. What does that mean? That party A, so there were 2 parties, party A and party B. Okay, A was the sender and B was the receiver. Okay, and A had, and they exchanged X Bitcoins. Okay, and A had at least X Bitcoins so that A could actually send X Bitcoins. And at the end of this, the balance of A came down by X Bitcoins, and the balance of B went up by exactly X Bitcoins. Okay, so there are, so the Zcash basically is a protocol which allows I and you to do such private transactions on Bitcoin, okay, arbitrarily, okay, and it scales at that level. Bitcoin is the largest cryptocurrency network in the world, right? And every example that I gave you is, it scales to the extent that is required in the industry today. Okay. Of course, there are always performance gaps between what you would ideally want and what the protocol is able to give, right? And the innovation always lies in taking that slightly imperfect protocol and adapting it to the industry scenario, to the practical scenario wherein it can be used.
Yes, I'm just trying to see if there are any more questions.
Okay, let me stop sharing. I don't think I will need to refer back to this.
Yeah, I don't see any more questions, so we'll stop here for now. Thank you so much, Dr. Vinayaka Pandit, for accepting our request to give this talk and making us familiar with these very topical terms like cryptocurrencies and blockchain, and and also showing us the relevance of blockchain in so many different fields. So thanks a lot for sparing your time and being with us this morning. And for the participants, we will meet again at 2 o'clock. So for now, we will stop this meeting here. Thank you so much.
Okay, thank you. I enjoyed myself as well. Thanks a lot for this opportunity.